Alright, we're starting section 6.4, which is improper integrals. The good news is if you're in my brief calculus course, this is the last section we are covering this semester. So what are improper integrals? Improper integrals involve infinity or negative infinity. We're trying to find the area beneath the curve on a given interval. Well, those intervals have always been numbers. What if one or both of those endpoints are infinity or negative infinity? How are we going to handle that? And that's what an improper integral is. So let's go ahead and read this together. It says the definition of a definite integral, the integral from a to b of f of x dx, or with respect to x, requires that the interval a, b be finite. In other words, a and b need to be actual numbers, not infinity or negative infinity. It says, furthermore, the fundamental theorem of calculus by which you have been evaluating definite integrals require that f be continuous on that closed interval. Some integrals do not satisfy these requirements because of one of the conditions below. It says one or both of the limits of integration are infinite. Or the function f has an infinite discontinuity at the interval a, or in the interval a to b. It says integrals having either of these characteristics are called improper integrals. In this section, you will study the integrals where one or both of the limits of integration are infinite. For instance, the integral 0 to infinity of e to the negative x dx. Well, if it was like 0 to 5, we could do it just by plugging in the number 5 and plugging in the number 0. But it's not as simple as plugging in a number infinity because infinity doesn't exist. So what do we end up having to do? Well, let's look at the picture of what we're doing. Here's the graph of e to the negative x. That graph is given to you in figure 6.13. All we're doing is saying find the area beneath the curve. And what you kind of realize here is as you get further and further to the right, that graph, the function value is so close to 0 that you're essentially adding no area. And as you go further out, it would be an infinitely small area. So it would be reasonable to think that this might converge to a finite number, that there might be kind of like an upper bound of what this area could be as we went all the way out to infinity. And so we can find this integral. We have to figure out how we're going to do it. They give us another example, figure 6.14, where they're finding the integral of 1 over x squared plus 1, and on this one they want to find it from negative infinity to infinity. And again, if you look at those tail ends, it's so close to 0 that you're adding virtually 0 onto the area. If you were thinking about back to the rectangle sections we were doing, you'd be having area of 0 on those endpoints, so or virtually 0, is close to 0 as we wanted it to be. So it's feasible to think that some of these are going to have values where they converge. There's also going to be some that diverge. For instance, let's think of the graph of the square root of x. So here's the graph of the square root of x. If I said, what's the integral from 0 to infinity of the square root of x dx? Well, that area is just going to get bigger and bigger and bigger and bigger, and this is going to go to infinity, an area of infinity, which is called divergent. So if it doesn't converge, if it doesn't come to a single number, we call it divergent. Okay?